So this is one of the last topic in the class, which is Taylor series. Recall that we have the geometric series, which brings us the following power series representation of a function, which also coincidentally gives me the expression of logarithmic log and arctangent, but it only have such but it can only carry us that far, and so we have to sort of like take a new perspective on how a power series is representing a function. So here, let's assume that I have a function f of x represented by a power series centered at a. So it would look like the following. Cn x minus a to the n. So right, this is a power series centered at x to the n, and suppose that it has a non-trivial interval, non-trivial radius of convergence, and that with radius of convergence r strictly greater than 0. Then what we can say is that, well, if the power series actually does represent the function, then the derivative of the power series, right? The derivative of the power series should also agree with the derivative of the function, at least on the points where the power series is successfully representing the functions. And we are going to choose not just any point on the interval of convergence, but we're going to choose a specific point so that our life can be made a lot more simpler. Namely, I'm going to choose the center where x is equal to a, and the reason will become apparent later. So let's first make an observation, which is that if I differentiate with respect to x k times to the power series Cn x minus a to the n, and then I evaluate everything, at the center x equal to a, then we're going to see almost all terms canceled, or like almost all terms vanishes. So first of all, let's look at the term. Well, let's look at Cn x minus a to the n for n is less than k. So what happened if I differentiate with respect to x k times? Well, this is basically a monomial. So by power law, what we're going to get is that every time we differentiate, the power decreases by 1. It will decrease to n minus 1 with the first derivative, n minus 2 to the second derivative. But the issue is that because n is less than k, so what this means is that, okay, for the differentiation, I'm going to get actually, I will not reach k. I will reach the nth derivative of this. Actually, n plus 1th derivative of Cn x minus a to the n. And then we will realize that once we take this many derivatives, this will have to be 0, no matter which point it is, because the nth derivative, if you take n derivative, then the power should decrease n times, and so you get 0's power, which is the constant. And then you differentiate it one more time, and you will get 0, because the derivative of a constant is 0. But the thing is that n is less than k, and so n plus 1 is less than or equal to k. So what this tells me is that for n is less than or equal, for n is less than k, what we'll get is actually nothing would remain. So if I take the kth derivative of Cn x minus a to the n, this would be 0. And if I take Cn x minus a to the n, and I take its derivative k times, but now I'm considering the situation where the inequality is flipped, where n is greater than k. So here is why taking the point x is equal to a can be very helpful, because, well, I'm going to take the derivative of x minus a k times, right? K times, but n is greater than k. So that means that uh, that after I take the kth derivative, what I will have is some coefficient, which we'll get into later, times x minus a to the n minus k. Well, note that this n minus k is greater than 0. And so you have a non-trivial power of x minus a, but then if you evaluate, that means that if you evaluate the whole expression, the kth derivative of this monomial, what you will eventually get is 0, because you have a non-trivial power of x minus a left behind, and when you plug in x is equal to a, then this thing x minus a will be 0, and 0 raised to any power, a positive power, is indeed 0. So that just leaves us with one scenario which we should anticipate, is that what happens when you take the nth derivative of Cn x minus a to the n. And this is quite interesting, because if I take the nth derivative, that means that the power should go down n times. That means that it will return to me a constant. And each time I take the derivative, this power n would come in front. And so that in some sense that I will have, so I take the nth derivative, I should have Cn times n times, well, x minus a to the n minus 1. But then I take another derivative. So the n minus 1 comes out, and I have an n minus 2. And then I take another derivative, then n minus 2 will come out, and so on and so forth, until I have just until I have something like this. So after I take n minus 1 derivative, what I will have is a linear x minus a to the first power, and then I take the nth derivative, and finally this thing will be vanquished, and then this will be multiplied by 1. And so this means that if I take the nth derivative of Cn x minus a to the n, what I will get is, in fact, n factorial Cn. It doesn't matter where I evaluate x, because this is a constant, but let's just, for the sake of completeness, let's say this is evaluated at a. And so with all our discussion, we see that, well, if I am in this ideal scenario where fx is represented by this power series centered at a with a positive radius of convergence, then what I can say is that, well, this power series actually encode the information of all the derivative of f, well, but only at the point x is equal to a. And it is encoded by the following formula, which is that, the nth derivative, denoted f superscript with a parenthesis n, at the point a is equal to n factorial times Cn. Right. So let's see an example. So we'll see an example, which is the one that we used, is f of x is equal to 1 over 1 minus x, which is equal to summation from n equal to 0 to infinity of x to the n. So, well, it's quite clear that in this situation, all the Cn's are 1 for all natural number n. So then let's see that our claim is true. So our claim is that the nth derivative at the center, well, this power series is centered at 0. at 0 is n factorial times Cn, which is just n factorial. And we'll see that it is true. Okay, so 1 over 1 minus x, let's write it as 1 minus x raised to the negative 1 power. So this is f of x. And if I take the first derivative of x, then what this will give me is by power law, 1 minus x to the minus 2 when the minus 1 come out. But what we realize is that by the chain rule, this minus sign should also fall out, so you have a positive. So the first derivative would give you 1 times 1 minus x to the negative 2 to the negative 2. By the same argument of like sign cancellation, if you take the second derivative, the negative 2 come out and the negative sign will be canceled out by the negative sign in the parentheses. So this will be 2 times 1 times 1 minus x to the negative 3, which is what the power law says. When you take derivative, the power go down by 1. And so on and so forth. So if you take the third derivative of x of f, then you will have the negative 3 comes out, where the negative 3 has the sign canceled by the negative sign inside. So what you have is 3 times 2 times 1, that 1 minus x to the negative 4. And then what we realize is that if we evaluate that x is equal to 0, then 1 minus x would be just 1, and 1 raised to the any power is 1. So we have f prime at 1 is 1, f double prime at 1 is 2 times 1, f triple prime at 1 is 3 times 2 times 1. And this actually agree, at least so far with this pattern, that the nth derivative is n factorial given by this formula. So, and it's not hard to convince ourselves that, judging by what we have done, that this formula holds true in general. So now that we have this information, our goal become reversing this process by computing the derivative of functions whose derivatives are easily computable and using the power series to sort of and use them as coefficients of power series, and hopefully that will represent the functions that we're trying to represent. So use derivative of f to construct its power series representation. So our model example would be exponential, cosine, and sine, because their power, the derivatives are easily computable, and there are values for which we can plug in into those functions, and that will return to us like simple numbers like 1, 0, negative 1. Again, we turn to our observation, which is that, well, if my function f is represented by a power series, then the relation between the nth derivative at the center and the nth coefficient of the power series is this. Let me box this. So hopefully, if we can compute all the derivative of f at a certain point a, then by the formula we have, fn nth derivative at the point a is equal to n factorial cn. What we can write is actually f of x is actually represented by the power series center at a and start at 0 of cn x minus a to the n. But in this case, because we have the relation of between cn and the nth derivative of f at the point a, what we can do is by substituting the following into the formula. Right. So our goal is to hopefully for some functions whose derivatives are easily computable, come to this conclusion or like a representation of that function as a power series. So the easiest example is exponential e to the x. And then if I let f of x denote e to the x, then we know that however many times you differentiate e to the x, you always get e to the x back. And we know that for any positive real number, actually for every non-zero number, if we raise it to the 0th power, namely if we plug in x is equal to 0, it will always return to us 1. So this tells me that exponential, if the exponential function has a power series representation, it should equal to the following. So by my formula, it's f to the n at 0, n factorial times x minus 0 to the nth power. So this will be summation from n equals to 0 to infinity, 1 over n factorial x to the n. Again, that's because at x is equal to 0, e to the 0 is 1. Okay. So and the fact is that the power series that I have written, which is x to the n over n factorial, converge to e to the x on all real number x, actually on all of r. So add all real number. And so, well, that's nice. So what this does is that it actually allows us to compute, like, say, what is E? What is the natural base E, right? So the natural base E, well, it is, well, you plug in x is equal to 1 into the function. It's the same as you plug in x is equal to 1 to the power series. So the natural base E is given by the following series, 1 over n factorial. And n factorial grows so fast. So basically taking the first like 8 or 7 terms, you will have a very, very high accuracy of E. Okay. Now, let's turn our eye to something that could potentially be a little bit more complicated, but still manageable. So let's look at cosine of x. So if I let my g of x to be cosine of x, then I know that my g prime of x is negative sine of x. G double prime of x would be negative cosine of x. And g third derivative, x, would be negative sine, would be positive sine of x, would be sine of x. And then, luckily for us, if I take the fourth derivative, the derivative of sine will return to us cosine of x. And so what we realize is that the sort of like the derivative of cosine, the lists of derivative of cosine would repeat itself after every 4 derivatives taken. That's beneficial. And if I plug in the value x is equal to 0, then I get the pattern 1, 0, negative 1, 0, right? And so that means that if I have the following power series representation of cosine of x, let's say cosine of x is equal to summation from n equals to 0 to infinity of some cn x to the n. So let me center things at 0. Then we know is that cosine to the nth derivative at the point 0 equals to n factorial times cn. But the thing is that we actually do know what is cosine, the nth derivative of cosine at 0. It is given to us by the pattern that we have. So that means that, well, cn is equal to cosine to the nth at the 0 over n factorial. Well, this I have to separate into 4 cases. So first of all, it will equals to 1 over n factorial for well, 1 over n factorial. That basically means that the nth derivative of cosine at the point 0 is 1. And it happens at no derivatives, fourth derivatives. And because the pattern repeats itself after every 4 times, after every 4 derivative, so we know that it will take the value 1 at the 8th derivative, the 12th derivative, so on and so forth for n divisible by 4. And what we're going to notice is that the first derivative and the third derivative of cosine of x at the point 0 would return to me 0. And I know that this pattern repeat every 4 derivatives. So this gives me the confidence to conclude that this Cn will be 0 for n odd. So for all odd number n, my coefficients of the power series would be 0. And so that leaves us with the last situation where I have -1 over n factorial. Well, this means that the cosine to the nth derivative would be, well, the nth derivative of cosine at the point 0 would be -1. And if we look at it, there's only one scenario where it happens, where we take the double derivative, where we take the second derivative of cosine and we evaluate it at 0. And then we know that the pattern repeat after every 4 derivatives taken. So that means that this is the second derivative. The next time the -1 will appear is at the 6th derivative and at the 10th derivative. So this number have a one thing in common, which is that they are even, but they're not divisible by 4. But not divisible by 4. And so what this tells me is actually, well, very nice. First of all, there is no odd coefficient for cosine. This is good. And that the coefficients alternate between 1 over n factorial and -1 over n factorial for even n, depending on whether it is divisible by 4 or not. So that means that if I'm trying to first of all, spin it in a more theoretical explanation is that I'm going to let my n to be 2k, right? Because I sort of know, I know from this thing is that there is no odd coefficient Cn. So that means that I will not see odd power n here. So we might as well, because we are working with all the even coefficients, we might as well set n to be 2k. So this tells me that C of n, which is C at 2k, is equal to 1 over n factorial for even k, right? So because if k is even, then k is 2 times L for some integer L, and so n equals 2 times k is equal to 4 times L, so it's divisible by 4. And -1 over n factorial for odd k. Right, so if k is odd, then, well, 2k, then k is equal to, say, 2L plus 1, and so 2k, n equal to 2k is equal to 4L plus 2. So because this 4L plus 2 for some integer L, that means that, well, this dangling plus 2 prevent n from being divisible by 4, right? Actually, let me redecorate the n, rewrite the n as 2k factorial, which I decided I'm going to use the 2k to represent in the place of n. So, well, this is also good because if something, because I know that the expression -1 to the k is equal to 1 if k is even, -1 if k is odd. And this tells me that actually C2k has a very concise expression, which is -1 to the k over 2k factorial. And so this tells me that the cosine of x can be written as the following power series from the summing from k equals to 0 to infinity of -1 to the k over 2k factorial times x to the 2k. And if you like, you can change this k into n, which will become a more familiar notation that we have been using. Okay, so this is cosine. And I guess this is a more sort of like a rigorous and systematic way of finding out what's the power series of cosine. Well, this is provided that the power series does converge. So this equality is currently a lie, but I'm going to tell you that actually, like the exponential, the power series of cosine converge on all of R, and just it does not converge to any arbitrary number. It does converge to cosine of x. So this is true for all real value for all x. Okay, so this is cosine. And then similarly, we're going to do sine. So suppose, let me just say, I have sine of x. I wish to discover its power series representation. And I'm going to use the same strategy, which is that I know that the derivative of sine behave very similar, like the derivatives of cosine is sort of the list repeat itself after every 4 derivatives. So sine of x, well, let's just say this sine of x to the 0th derivative. And the first derivative of sine will give me cosine of x. The second derivative of sine will give me negative sine of x. The third derivative of sine will give me negative cosine of x. And so the fourth derivative of sine will give me sine back. And so we see that indeed this list will repeat itself after 4 derivatives, right? Because we return to sine. And if I take the fifth derivative, it's basically taking 1 derivative of the fourth derivative. And so the pattern must repeat itself after 4 derivatives. So, and if I evaluate at x is equal to 0, then I have 0, 1, 0, -1. And 0, 1, 0, -1 for the next 4, 0, 1, 0, -1 for the next 4 terms. And the pattern will repeat infinitely. So again, our trick is that if sine has a power series representation, then it has to be from the sum from 0 to infinity of sine to the nth derivative at 0 over n factorial x to the n, right? But the question is that can I write it in a more concise way? And in fact, we can. So here I'm going to use a method kind of different from like the previous one, which is that I'm going to realize that sine to the nth at 0 is going to be 0 if n is even, right? Because we know the 0 from the 0th to the 3rd derivative, sine evaluated at x equal to 0, the thing will return to me 0 at the 0th derivative and the 2nd derivative, and the pattern repeat like every 4 things. So you know that like you can predict that you get the 0 at every even order derivative, and we know that it's going to be 1 if n is equal to 1, and then it's going to repeat itself after every 4 times, so 5, 9, so on and so forth. And this thing has this number have one thing in common, which is that the remainder when divided by 4 is 1. And so it will be, and then similarly, -1 if n is equal to 3, again, 3, n is equal to 3, and then the pattern repeat every 4 derivative, so 7, 11, so on and so forth. And then these are the numbers who has remainder when divided by 4 being 3. So very similarly, I will not be content with this expression. So I'm going to pretend my n is equal to 2k plus 1. And the reason behind that is I know that I will only have a non-zero number at when n is odd, and so I will have n is odd, and I want my power series to start at k equals to 0. So I will pick 2k plus 1 so that when n actually starts at 1, k starts at 0. And so sine of 2k plus 1 of 0 would be, well, first of all, let's say if k is even, right? So if k is even, k is equal to 2l. And so 2k plus 1 will be equal to 4l plus 1. And 4l plus 1, judging by this expression, we know that when it is divided by 4, the remainder will be 1, which is the case that I have here. So then that means that I should have positive 1. And I know that it will have negative 1 if k is odd. That's because if k is odd, then k is equal to 2l plus 1. So 2k plus 1 is equal to 2 times 2l plus 1, which is 4l plus 3. And judging from this expression, we know that when this number is divided by 4, the remainder will have to be 3. And I know that for this orders of derivative evaluated at 0 for the function sine, will return the value negative 1. So, and then again, the trick is very similar, is that I can write this as no cases now, negative 1 to the k, right? Because if k is even, negative 1 to the k is 1. If k is odd, then negative 1 to the k is negative 1. So in short, what I can write is that if sine has a power series representation, then it will have to be from the following, from k equals to 0 to infinity of negative 1 to the k over 2k plus 1 factorial times x to the 2k plus 1, right? That's because I let n be 2k plus 1, and I discovered that sine of n at these various values of k obey the following formula. And you see that no even term appear in this power series is basically because the power the even order derivative of sine evaluated at x equal to 0 will always give me 0. And so they don't actually have to, they shouldn't appear here at all. And this is actually the most concise way for me to represent sine as a power series. And just like exponential and cosine, this equality actually holds for all real, for all values of x. So these are the three main examples that we can obtain by basically say I take the derivatives of these functions so many times and I obtain a power series representation. Right. Okay. So, and the last thing that I was really interested in doing in front of you guys are pretend, this is a big pretend, I can plug in complex value into my power series. And you should pretend. I don't need to pretend because I know that I can. So you may need to pretend that you can. But then we're going to do that and sort of do an exercises in identifying the coefficients of power series and sort of like do an exercise in that and see that the Euler formula is indeed true in its power series form. Right. So let's start with e to the ix. This is by my formula, and by the power series representation of exponential ix raised to the nth power over n factorial. Okay. And so I is the imaginary unit, I squared to -1. So actually, let me just write it as I to the n here over n factorial times x to the n. So we know that I squared to 1, and that means that I cube, which is I times I squared, is -I, and I fourth is I times -I, which will be 1. So I1 will be I. And if you like, and I to the 0th is also 1. So you see that the sort of like the integer powers of I also has a repeating pattern, like after every 4 terms, right? So all the so the 0th power, the 4th power, the 8th power, so on and so forth, will give you 1. The 1st power, the 5th power, and the 9th power, so on and so forth, will give you I. And so like for the 2nd power, the 6th power of I, they will give you -1. The 3rd power, the 7th power, a -1. The 3rd power and the 7th power, so on and so forth, will give you -I. So that means that I want to sort the coefficients by real and imaginary. So I'm going to sort my real coefficients into one series and the imaginary coefficients into the other series. And I claim that if you sum this to series, it will be the same thing. And that is because the series converge absolutely. So I can do this rearrangement, which is very important. So let's say I to the n, let's summarize the pattern, will be I if 4 is divisible, n is divisible by 4. No, 1 if 4 is n is divisible by 4. I if sort of like the remainder when divided by 4 when is 1 and -1 remainder when divided by 4 is 2, and -I when remainder when divided by 4 is 3. Okay, that's good. So I know all the even thing will appear at so I know all the even thing, all the real thing will be concentrated on the even term, and all the imaginary thing will be concentrated on the odd term. So that basically means that e to the ix is equal to okay. So let me is equal to right. So let me sort the real thing here. This will be summation. I will shift to k again, k from 0 to infinity of -1 to the k over, well, 2k factorial x to the 2k. This is the real part, and the imaginary part is I, k from 0 to infinity of -1 to the k, 2k plus 1 factorial x to the 2k plus 1. Right. And this is because if I want to sort all the real thing, right? If I want to sort all the real thing, I realize that all the real thing are concentrated at the eventh power. So I'm going to change my index. I'm going to sort of like make my n to be 2k because I know that this will only appear at even n. So the most efficient way for me is to write it as 2k. And I know that it will appear for every even number, right? Not just 0, but 2. And because the pattern repeats itself, well, so like 4, 6, 8, so on and so forth. So making this choice is reasonable. And then what I realized is that if 4 divides n, that means that 2k is divisible by 4, and by similar reason as above, k must be divisible by 2, right? Because 4 is divisible by n, so you take away the 2, so basically 2 divides k, so k is itself even, and if k is itself even, it will return to you 1. And similarly, if k is divisible by 2 but not by 4, that basically means that 2 must be odd. Because if that means k is odd, so that basically is like the argument that I used as before, is that k is somehow equals to 2l plus 1, and you multiply it by 2. So you have 2k equals 4l plus 2. So these are precisely the even numbers that is not divisible by 4. Or in other words, the numbers that when you divide it by 4 have a remainder 2. And similarly, if I look at all the imaginary thing, I know that the imaginary terms will be concentrated at the odd powers or at the odd terms. So I'm going to shift my index. I'm going to rename my index n as 2k plus 1. It makes sense because I know that it appear, the imaginary thing appeared at every odd power, and that an odd power only and every odd power. So making this choice makes sense. And I know that it's positive I when divided by 4, the remainder is 1, and negative I when divided by 4, the remainder is 3. So that means that if k is itself even, so k is 2l, then 2k plus 1 is equal to 4l plus 1. So you might have seen this a couple minutes ago. These are precisely the numbers when you divide it by 4 has a remainder 1. And we know that for this number, I should have a positive I. That means that this negative 1 to the k had better be a positive 1. So that means that k must be even, and it's in fact what we have. So our logic closes itself. And that similarly, when k is odd, so basically when this power is increased by 2, right, from 1 to 3, so k will be increased by 1. So basically, if k is increased by 1, then 2k plus 1 will be increased by 2. I know that when this is increased by 2, you pick up an extra negative sign. So, well, this is actually the correct thing to look at. And if you look at your notes, or actually let me just look at it for you, is that cosine of x is the following series, right? And it is in fact the same thing that appeared here. And sine of x is actually this following series, right? Sine of x is actually this, is the same thing. So even when I plug in the complex values, I see that the Euler formula is true in the form of power series. So I'm going to sort of give you a few definitions, right? Which is if f of if f is represented by the following power series, n from 0 to infinity of Cn x minus a to the n, then we call this the Taylor series of f centered at a, and if the Taylor series is centered at 0, then we just call it the Maclaurin series. This is the so for exponential sine and cosine, what we have been doing is actually Taylor series centered at 0, also known as the Maclaurin series.